So we're going to illustrate the use of the Buckingham-Pi theorem by taking a look at the pump scaling laws. In particular, we're going to look at the dimensional analysis that goes in behind the pump scaling laws. Where do those pump scaling laws come from? Well, they come from applying the Buckingham-Pi theorem. What we're going to focus on is one of the three main pump operating parameters that we've been talking about in class. Those three parameters are the head produced by the pump, the flow rate through the pump, and the power requirements of the pump. So as an example, we're going to look at the power requirements of the pump. So the Buckingham-Pi theorem starts by identifying what the dependent variable is. So in this analysis, the dependent variable is the so-called brake horsepower, or the shaft power. And the next thing is to identify the independent variables. So we're supposing that that shaft power is a function of the following variables: the flow rate through the pump, the size of the pump as represented by its impeller diameter, the speed that the pump is turning at, n, the density of the fluid, the viscosity of the fluid, and finally a roughness parameter that represents the roughness of the impeller blades and the inside surfaces of the pump. So this is how Buckingham-Pi theorem always starts: a dependent variable and a list of independent variables. The next thing is to just simply count how many variables we're dealing with. 1, 2, 3, 4, 5, 6, 7. So in this analysis, n is equal to 7. Next step is to take all of these variables and figure out what their dimensions are. So we're going to do that next. So starting with our dependent variable, this is power, but we need to express this in terms of basic dimensions. Now the way I usually do that is I actually start with units because we're just a little more familiar working with units. And we'll start with the unit for power, which is a watt. So watt is not a fundamental unit, so we need to break this down until we have only fundamental units. So a watt, remember, is a joule per second. Still not in fundamental units. A joule is a Newton meter, so this is Newton meters per second. Still not in fundamental units. The Newton needs to be broken down into a kilogram meter per second squared, and we need to remember we have meters and seconds there as well. And so finally, collecting that all together, this is kilogram meters squared per second cubed. So now we can put this in terms of its dimensions. So power is mass L squared over T cubed. Mass, length squared over time cubed. So that's our power. We need to do the same thing for the rest of the parameters. And so we have Q. Remember, Q is a volume flow rate. Well, that's just L cubed over T, volume flow rate. Diameter is simply L. N, so N is a frequency. Whether it's radians per second or RPM, those are all just units. But in terms of dimensions, it's 1 over time. Density is mass per unit volume. Next is viscosity. So for viscosity, we'll do a similar thing that we did up here. Viscosity, this is dynamic viscosity, so it's Pascal seconds. Again, not fundamental units. A Pascal is a Newton per meter squared. Still not fundamental units. A Newton is a kilogram meter per second squared. Keep our seconds and meters squared here. Now we've got it in fundamental units. Just gather them together. So that will be kilograms over seconds and meters. So our fundamental dimensions then are m over LT. And then finally, the last one in our list is the roughness, and of course that's just a length. So we take a look at this whole list and we see that it involves M, L, and T. There's no temperature here, there's no Q. So there are 3 dimensions involved here. So we say J is equal to 3. And so N minus J is equal to 4. So we will expect 4 dimensionless groups to come out of this analysis. Next thing we need to do in the Buckingham-Pi theorem is choose our repeating variables. So go back up to our list here and consider which ones we're going to choose. So remember, we don't want to choose our dependent variable as one of our three repeating variables because we don't want that to appear in every one of our groups. We're trying to find this as a function of other things. We don't want it to appear in more than one place. The other consideration is we want to pick variables that are convenient to appear in multiple groups. And so we're going to pick the diameter, the speed, and the density. I don't want the flow rate to appear in multiple groups because I want to find the dimensionless flow rate coming out of this. I don't want it to appear multiple places. So I'm going to pick D, N, and rho. Now notice we also need to make sure that those do not form a dimensionless group by themselves. Well, realize that neither D nor N involve mass. So there's no M in either of those, but rho does have mass in it. So that means that it's impossible to form a dimensionless group just with those three. So we're going to select D, N, and rho as our repeating variables. So we'll say that here. D, N, and rho are the repeating variables. So we're ready to find our dimensionless groups. And we'll start off with pi 1. And usually we start off with the dependent variable. So we form our first dimensionless group. First of all, we take our three repeating variables and raise them to three unknown powers. So d to the a, n to the b, rho to the c, and then we put our dependent variable here, our brake horsepower. So that is going to be a dimensionless group, and it's just a matter of finding the powers A, B, and C required to make this dimensionless. So the way we do that is we go and get the dimensions for each of these. So the dimensions of diameter is length, raise that to the power A. The dimensions of the speed is 1 over time, raise that to the power B. And the dimension of density is mass over volume, raise that to the power C. The dimensions of the power is ml squared over t cubed. So that has to have a 0 exponent on mass and on length and on time. This is just a way of saying it has to be dimensionless, that all of the powers of m, l, and t have to add up to 0. So that's what we do. We form three equations with three unknowns. So we start with m. So we're just looking for m's here. No m there, no m there. Here we have an m raised to the power c. So we're adding all of the powers of m. So we start with a c. Here we have m to the 1. So c plus 1, and of course that equals 0. So this tells us right away that c is equal to negative 1. So we found one of our powers. Next we do L. Same thing. Here we have L raised to the A. So that's A. No L involved there. Here we have an L cubed, but it's in the denominator. So we need to make sure we put minus 3C. And here we have an L squared. So that's plus 2 equals 0. So notice we've already found C, it's negative 1, so we could actually find our A value right away. So this A is going to be equal to, moving this 2 over here is minus 2, moving minus 3C over the other side becomes plus 3C. However, this is negative, so this is minus 3, so A is equal to negative 5. Last one is T. Again, just adding up the powers, no t there. There's a minus b, no t here. Here's a t cubed, so minus 3 equals 0. So b is equal to minus 3. So we have our three unknown exponents that we've found there. So now we can form this dimensionless group. We can say pi 1 is equal to, and you'll notice they're all negative, so all of those are going to be in the denominator. So we can just write our brake horsepower, just rewriting that, and then the rest of these things are in the denominator. Density is to the minus 1, so put a row there. The speed, b, is to the minus 3, so n cubed, and then finally d to the 5th. So that is our first pi group. And this tells us the appropriate non-dimensionalization of shaft power, or of brake horsepower. Rho n cubed d to the 5th. So this is the first of our pump scaling laws, essentially. So that's the first of our 4 dimensionless groups. So we just repeat this process 3 more times. So we'll go through this. Pi 2, so the same repeating variables. So that part is exactly the same as for pi 1, but now I go and I get one of the other variables that we haven't used yet. So we're going to put q here as our next one. And then again, we go and get the dimensions. Now the first 3, of course, are exactly the same as before, because the repeating variables are still the same. So all of that is the same every time. And then q is L cubed over t. And that has to have no dimensions. So our mass powers, no mass, C, no mass equals 0. So that tells us C equals 0 right away. And notice density is the only one of these parameters with mass in it. Therefore, its power has to be 0 so that it's not in the dimensionless group. Because we can't have it in there, it's the only one with mass in it. Next is L, and it doesn't matter what order you do these in. There's an A because we have an L there, no L there, minus 3C. And of course that's the same as before. But then here's an L plus 3 equals 0. Well, notice we've already found out that C is 0, so that's gone. So this tells us A is minus 3. And then finally T, we have no T here and a T in the denominator here. So that's minus 1 equals 0. So this gives us B equals minus 1. So those 3 things tell us what our second pi group is. So pi 2 is equal to Q, so that's this Q, divided by, and again notice they're all negative, except for this one that's 0, n d cubed. So that's our second pi group. So again, for pi 3, same repeating variables, d to the a, n to the b, rho to the c, and now we'll put viscosity here. And again, go and get the fundamental dimensions of these. And viscosity is m over lt. Mass, c plus 1 equals 0. So c is equal to negative 1. So notice there's no mass, c there and a 1 there. L, we get a for this L, no L there, minus 3c, notice that's the same, and 1 L in the denominator, minus 1 equals 0. Notice we already know that c is equal to negative 1, so that gives us a equals minus 2. Finally, we have t, and no t there, minus b, no t there, and minus 1 equals 0. So b is equals negative 1. And so our pi 3 is equal to mu over d squared n rho. Now, if we take a look at this, this is actually a Reynolds number. So what we're going to do is one of our group manipulations here to make it look more like a Reynolds number. I'm going to just invert this. And remember, we're able to do that because we can raise any group to any power we want. Well, I'm just raising this to the power minus 1. So that becomes rho n d squared over mu. So this is our third pi group, and it's really a Reynolds number. The velocity that we normally see in Reynolds number is made up by the speed and one of these diameters. Because an angular speed times the diameter gives a velocity, a tangential velocity, and then the other d is the length scale. So that's the first 3 dimensionless groups, and the fourth one Happens very, very quickly here. The fourth one, again, same three repeating variables. Epsilon is our last remaining independent variable here. So we get L to the A, 1 over T to the B, M over L cubed to the C. That's the same as always. Epsilon is just L, and this has to be dimensionless. This is one of those cases where the parameter we've put here is just a length scale. So notice what has to happen here. This is the only thing with a t in it, so b has to be 0. This is the only thing with an m in it, so c has to be 0. So these two are essentially gone. That a has to be -1 to move this L in the denominator. So this tells us that a equals -1. And so our pi 4 group is just epsilon over d. So the relative roughness shows up as a pi group here. So now that we've found all four dimensionless groups, the last thing to do is just restate the connection between the dependent variable and the independent variables in dimensionless form. So our dependent variable was the brake horsepower, and we found that it was non-dimensionalized by rho n cubed d to the fifth. And that is a function of three independent variables. One is the flow coefficient, and that is, go back and look at what that one is. That one is q over nd cubed. So this is nd cubed. And then we had our Reynolds number, which was rho nd squared over mu. And then finally the one we just found, the relative roughness. So that's the conclusion of the Buckingham-Pi theorem, and it converts a function that is in dimensional form and guides us towards the appropriate dimensionless groups for this problem. Now in this case, this leads us to the pump scaling laws, because this is called the power coefficient and this is called the flow coefficient. And if we have two geometrically similar pumps, those dimensionless groups are going to be the same between them, so we can use them to scale different characteristics of those pumps.